Diffusion, the international science radio show.
We have a bouncer on the doors of perception.
The good, the bad, the ugly.
It gets pretty exciting.
The myths, the truths.
Toxicology.
Astroseismology.
Magnetism. The dark side.
Genetically engineered potatoes.
Planetoid.
Planetoid.
I love that word.
Hello and welcome to Diffusion. Sit back and relax while we synthesize your brain with weird and wonderful science. I'm Ian Woolf. On this edition, Burt talks about organo-metallic chemistry. But first up, here's news of something strange in our planetary neighbourhood. Life on Venus? An international team of astronomers led by Professor Jane Greaves of Cardiff University, working at the James Clerk Maxwell Observatory in Hawaii, have detected phosphine in the atmosphere of Venus, and have concluded that it just might be a sign of something living in the atmosphere. The surface of Venus is too hot for life at around 400 degrees Celsius, but at around 50 or 60 kilometres up from the surface, parts of the atmosphere are only 30 degrees. There's also water in the atmosphere. Either the phosphine is produced by some weird chemical reactions we've never seen the like of before, or it's being produced by some kind of life. Atoms and molecules absorb light at very specific and unique wavelengths, and the resulting absorption spectrum revealed a gap at the wavelength of phosphine, like a shadow. This implies that phosphine was present and absorbing light as it passed through the atmosphere. The observations in Hawaii were confirmed by further observations from the Atacama Large Millimetre Submillimetre Array in Chile. In the end, both observatories had seen the same thing: faint absorption at the right wavelength to be phosphine gas, where the molecules were backlit by the warmer clouds below. The original observations were recorded in 2017, but it's taken this long for the team to analyse the data, replicate them on another telescope, and be certain of the results. Phosphine, pH3, is a short-lived, toxic, flammable gas that smells like a combination of garlic and rotting fish. It breaks down from the oxygen in the air and oxygen in rocks. There are bacteria that make phosphine high in the air on Earth. So why did they look for phosphine? Team member and MIT researcher Dr. Clara Souza Silva had thought about searching for phosphine as a biosignature gas of non-oxygen using life on planets around other stars, because normal chemistry makes so little phosphine. If you find it on gas giants, it's no big deal. But if you find it in large amounts on rocky planets, then it can only be made from life or industry. On these rocky worlds, phosphine would be rapidly destroyed in their highly oxidized crusts and atmospheres. Venus turned out to be an excellent example. She published a paper about her ideas in the journal Astrobiology titled "Phosphine as a Biosignature Gas in Exoplanet Atmospheres." The team intended their observations of Venus to show what the atmosphere of a rocky planet without phosphine would look like, so you can imagine Dr. Souza Silva's surprise when the results showed lots of phosphine. On Earth, phosphine is produced by volcanoes and lightning, but only in very small amounts. Much larger amounts are made by human industry using processes that don't occur naturally, and by bacteria. On Earth, bacteria can absorb phosphate minerals, add hydrogen, and ultimately expel phosphine gas. Massachusetts Institute of Technology scientist Dr. William Baines led the work on assessing natural ways to make phosphine on Venus. Some ideas they tried included sunlight, minerals blown upwards from the surface, volcanoes or lightning, but none of these could make anywhere near enough phosphine to account for what they saw. Natural sources were found to make at most 1/10,000th of the amount of phosphine that they saw from the observatory. The problem for bacteria in the air of Venus is that it's 90% acid, whereas bacteria from Earth can only cope with 5% acid, even extremophiles. This also means it's extremely unlikely that any bacteria from the space probes sent to Venus in the 1960s, 70s and 80s spread bacteria that produced the phosphine. The last NASA mission exploring Venus was in 1990, when the Magellan spacecraft mapped the planet's surface before plunging through its atmosphere to burn up. In 2006, Venus Express from the European Space Agency orbited Venus, and in 2015, Akatsuki from the Japanese Space Agency orbited Venus. Both spacecraft were used to study different aspects of Venus's atmosphere and weather. Venus is thought to have had temperatures and acidity friendly to life 1 billion years ago, before a strange event caused the carbon dioxide in the rocks to escape into the atmosphere and caused a runaway greenhouse effect that raised the surface temperature to 400 degrees Celsius and filled the air with acid. Our best guess is that volcanic events transformed Venus 1 billion years ago, but we're not certain. Phosphine has been detected on Jupiter and Saturn, where there's lots of high-pressure hydrogen available. Venus doesn't have any free hydrogen floating around, so the same processes can't be at work. The team's next step is to search for other chemical signs of life in the atmosphere of Venus. The instrument used to detect the phosphine is the same instrument that also took part in capturing the first ever image of a black hole. This instrument has since retired and has been replaced by a new and more sensitive instrument. This will be turned towards Venus. Ultimately, we need to send a new robot probe to Venus to look more closely. In their paper, the team conclude, if no known chemical process can explain pH 3 within the upper atmosphere of Venus, then it must be produced by a process not previously considered plausible for Venusian conditions. This could be unknown photochemistry or geochemistry, or possibly life. Even if confirmed, we emphasise that the detection of phosphine is not robust evidence for life, only for anomalous and unexplained chemistry. It's still exciting to think about. The paper is titled Phosphine Gas in the Cloud Decks of Venus and was published in Nature Astronomy. You're listening to Ian Woolf on Diffusion Science Radio. Send emails to science@diffusionradio.com. We're brought to you across Australia on the Community Radio Network and podcast over the internet on www.diffusionradio.com. How can you make the smallest wires for the world's smallest electronics? Liam Burt is a chemist. He's not the person who sells you your medicines, but perhaps the person who makes some of your medicines. Liam is an organo-metallic synthetic chemist. I spoke with Liam by Zoom and began by asking him, how did he get interested in chemistry?
So I got interested pretty much just in the hard sciences in maybe late high school kind of thing. Particularly, I'd always been interested in like my sciences, my maths and things like that. However, I had a very special mentor who was able to answer a lot more of my questions because I was a very inquisitive, to be correct. I was very inquisitive, had lots of questions, probably a little bit annoying at teachers, but I had a special teacher at the end of high school who was able to answer those questions as a former chemist himself. And so it was kind of like around year 9 or 10 where I thought to myself, I actually really like chemistry and physics. I want to start doing some of my own experiments.
And when did you start to specialise or get interested in the more complicated things like the organic, metallic, synthetic chemistry?
So it was kind of just an affair of, I guess, narrowing down my interests 1 year at a time. So if you want to say, like, let's start at year 12, I was interested equally in maths, chemistry, physics, and biology. So, of course, I went into first year of university and studied all 4 of those things. And at the end of first year, I thought, we're going to have to start eliminating some variables here, as every good scientist does. And Unfortunately, at the time, I still thought it was very interesting, but biology was the first one to go, so to speak. In second year, I knocked off maths. And then right at the end of my degree, end of my first degree, I had physics and chemistry left. And then obviously I've tried my absolute hardest to hold on to both of them because I was really torn between the two. But I did choose chemistry in the end, but I managed to hold on to just a little bit of physics as well. And so in my fourth year and my first official research project, I guess, I was doing synthetic chemistry, but in terms of doing photochemistry. So being able to take light, what you might have as visible light from the sun, and convert that into new chemical bonds. So yeah, pretty much at the end of my first degree, I was a chemist. However, I held on to just enough physics to tide me over. And of course, a couple of years ago, I started my PhD, and it's been pretty much chemistry since then. Yeah.
And so what is it you're studying with your PhD?
So I've always been really obsessed with, which I'm sure we'll get to at another point as well, is for me, I really want to know fundamentally how chemical bonds work. And that might seem like a really simple idea, and it might seem that might be very easy to go and study as an idea, but that's not really the case these days. So I came to where I am now at the Australian National University to study under my boss, who is one of the experts in metal-carbon multiple bonds. Metal-carbon single bonds are actually quite common, but as soon as you go to a metal-carbon double bond, they become increasingly rarer. And for me, I look at metal-carbon triple bonds, which are far more rare. So I guess that's sort of what I got into as far as like a very broad area, especially anything to do with metal-carbon triple bonds I want to look at, like I mentioned. However, I also want to now look one step further. If we've got a metal-carbon triple bond, for any people that have done some sort of chemistry, you might be thinking to yourself, okay, Liam, well, carbon tends to have 4 bonds. So what's on the other side? So as rare as metal-carbon triple bonds are, often the one bond that is left over is bonded to another carbon, or some like carbon, nitrogen, oxygen, something that's organic, but very, very, well, 4 or 5 people in history have asked the question, well, what if we put that missing carbon bond onto another metal? So a metal-carbon-metal spine is what I look at. They're incredibly rare. Out of the millions and billions of possible chemicals that there are, as of the other morning, I can tell you there are 129 of those molecules, which I've collated and looked at very closely. And out of those, around about 120 molecules, only 40 of them have a metal-carbon triple bond in them, and I've made around 25 of them. So quite a specific thing there, but, you know, it's the sort of start of a problem, I guess, which a lot of researchers nowadays are always working towards very noble goals. You know, we're trying to solve cancer. We're trying to save the animals inside of Antarctica. These very easy to see problems, and we know lots about those areas. And so they're at the end where they're trying to solve the actual problem. Whereas me, I'm right at the start. I'm just trying to understand, almost like a chemical explorer, what can we do, what can't we do, and then I look at problems much later on. So for me, I build these molecules. I'm currently testing their reactivity. So what happens if you have a molecule of these rare metal-carbon triple bonds sort of thing, and what happens with literally every other molecule? Do they interact? Do they form new things? And I see what comes out the other side. But I guess if all my wild dreams had to come true, you might think to yourself, okay, you've got this nice little spine, and we know that metals conduct electricity. So you might think to yourself, if you've got a metal-carbon metal bond, if we antagonize one of those metals with some electrodes, we might be able to put some electrons and change their electronic properties, and those electrons might be able to jump onto the carbon and then jump onto the metal the other side. And that's a very, very new type of area that's been up and coming maybe in the last 8 to 15 years, and it's definitely not been done on these metal-carbon metal bonds, as opposed to metals with 6 or 10 or 20 carbons in between them. These very small atomic wires, a lot of those have been done, but because no one has these much shorter chains like I do, that's what I would like to look at. So if they conduct, you could imagine the smallest atomic wires possible, which means you might be able to get the best electronics possible. If I had a very altruistic goal, that's what I would like to happen.
That's amazing. So the properties you're mainly looking for is conductivity in these new compounds.
Yeah, that's the main property we're looking at. There's also lots of, because we don't have these molecules, we don't know how they react properly. However, we have seen these carbon atoms in between lots of different metal atoms before. So if you've ever driven a car and you've used petrol in your car, petrol refinement is done via one of these special carbons in amongst a bunch of tungsten atoms sort of thing and other metals like that. And so obviously that's a massive process that everyone uses, and we know that it works and we get petrol out the other side, but we don't know perfectly how that happens. So you never know. Maybe I might be able to contribute to solving a little bit more of that problem as well. The other big one, of course, is the biggest chemical process around, the Haber-Bosch process, which is essentially a man-made version of how plants take nitrogen from the air, put it in our fertilizers, make our food, and it feeds humanity like we've never been able to imagine, especially 100 years ago. But we still don't know how those plants take up the nitrogen properly, and we haven't been able to emulate that. We're now at a point in the last 3 years that we have found that inside of plants, there is one of these rare single carbons in between 6 ions. So 6 ions in like a 3D diamond type shape, and at the center of that diamond is this single carbon. And we've seen it in nature, but we haven't been able to replicate it in the lab. Wouldn't it be great if we could? Hello, here I am. Let me have a go. So yeah, that's some of the more of the reactivity that we would like to look at to solve some problems if we could get a little bit further. Yeah.
And so what does your average day in the lab look like?
Thanks, Ian. That's my favorite question. A lot of people get caught off guard with this one, actually, because, you know, a lot of people are used to like a 9 to 5 sort of work. That's what we think of a work day. So surely you could split up every hour between 9 to 5 and it would work quite nicely. For me, as not just a chemist, but an organo-metallic chemist, metals often take much longer or much shorter if they're silly reactive, typically much longer than normal chemicals to react with one another. So my typical day actually starts at 4 p.m. the day before. So 4 o'clock, you've probably got an hour and a half until it's time to go home. I set all my reactions up there so they can react through the night, and I can come in first thing at 8 or 9 the next morning and see what's happened. So I react mine overnight. They react slow enough that I don't need to come in through the morning and observe them. I can infer that information later. And then you can sort of split the day up into a couple of parts. So I'll spend the morning as soon as I arrive, just letting everything cool down. We often have to heat these things up to encourage them. And so for that first little hour, I come in, look at, make observations, and then let them cool down and probably read some papers of what other scientists in my area have been doing. Shortly after that, everything will have cooled down. I'll have written down, yellow changed to orange. Some of the liquid has evaporated, all these kinds of observations, and I'll have a bit of an idea of whether things have worked or not. I'll be able to, say, evaporate down some solutions, make up some special samples. I'll put them inside of massive magnets to look at interesting properties that way, and that can tell me some information. It's not really a laser, but I can use an infrared beam is another way that I might look and see whether a mixture has converted to something else, and gather all of these little pieces of information across lots of different parts of my molecules to build a whole picture of what's happened, probably by lunchtime. I'll have made some sketches, and then shortly after lunch, I will prepare what's called a silica column. If you imagine like very fine sand, you can put a crude mixture on the top of that and use things like petrol or nail polish remover, which is acetone, lots of different solutions like that to separate them out. So something that's black or brown is not often black or brown. It's some red, some blue, some green, and all those different colors. I want to get them pure and on their own. And I spend probably half of the afternoon trying to separate all those colors out because they're all different new compounds. And then I guess while this is happening, I'll be looking at the things that I made the day before, analysing them, building up that story again. And then that brings us pretty much around to 4 p.m, made some new molecules, I've purified them, and it's time to analyze them through my spare time for the rest of the week, I guess. And that's pretty much what a day looks like for me. Obviously balancing some meetings and some teaching and stuff like that. That's pretty much my day as an organometallic chemist.
And you've been involved with Science Week and Young Tassie Scientists.
I have, yeah. I've been involved with a lot of National Science Week projects for quite a while, but of course, my true love and joy was my first organisation, the Young Tassie Scientists. So I've been with them. This is now my 5th year as a part of that program, which is quite long for a lot of people. This program is run down in Tasmania primarily by PhD students. However, so people that are in their 4th year or 5th year and probably to their 7th or 8th year of university as researchers. Having said that, though, I was quite a keen bean when I arrived at the University of Tasmania a few years ago. And so I came across this group through friends, and I love science communication. That's my other big love. So they let me straight in, and I've been doing it ever since. So I guess the objective of the Young Tassie Scientists is that we travel around to schools and we communicate these advanced research ideas and the wonderful things that we see as researchers, but in layman's terms, especially, we want to make sure that everything that we do as researchers, we can communicate to someone who is in kindergarten, someone who's in year 5, year 10, year 12, parents, all the way up to our grandparents. We want to make sure that it's as easy to understand as possible so we can share all of the cool things that we get to see as researchers.
And this year, did you prepare some videos?
I did. So the previous few years, I've really prided myself on trying to build models of never seen before things inside of classrooms. So of course this year that was made a little bit more difficult because of COVID. And of course I'm now stuck in Canberra. I wasn't able to make it back down to Tasmania because of that. So I went and made some videos this year. So of course I made some videos of, taking people through the lab. This is what my day looks like. But of course, I really love precious metals and I can't stop talking about the periodic table. So I made a small little mini series of 4 to 5 episodes this year of my little web series called Treasure at Home. So not only can I send people around their house to look at interesting items, I can teach them about the periodic table as they go. And of course, in the name, Treasure at Home, I want to send people around their house to try and find the rarest, most precious, expensive elements that I can that are actually hiding right before their eyes. And of course, in episode 1, we covered what is quite probably the easiest because people don't know that there's lots of it in their house and everyone knows how rare and expensive gold is. So wouldn't it be great to find some of that? And yeah, as a bit of a hint, we found quite a lot and there's quite a lot actually living probably behind your TV cabinet. But that was my little web series that I did this year, Treasure at Home.
So you go to classrooms and you've been building models and you've been doing videos. What's next?
So for me this year, I've sort of wound up, especially being outside of Tasmania. The Young Tassie Scientists primarily do their work there, and obviously we move online. So this year it's been a little bit impeded as far as myself personally with the program. But of course, I've done another four years of that beforehand, and I've done so many things for the program. So one of the coolest things that I've got to do is be a science show demonstrator for the Festival of Bright Ideas, or FOBI. It's down on the Hobart Wharf. There's lots of science companies and organisations that come together all under one roof over a weekend to show what they do. And I gave a few science shows assisting the great Dr. Jeremy Just, who is also a Young Tassie Scientist and who has done a lot of work with Questacon as well. So I got to do that a couple of times to make lots of explosions, lots of bubbles, all sorts of stuff that you would expect with a magnificent science show. So that's probably the coolest thing I've done. I also go around to schools as well and act as a judge in their science competitions. So when you're in like year 9, 10, 11, 12, you might be doing like these young investigator type programs where obviously you have your science classes, you prepare a poster, and I would come around as a guest judge, especially for chemistry and physics types problems, just to come around and assess and everything of, this is a cool poster, this is a cool idea. And then also, to be able to sit down as a researcher myself and start to ask those important questions, like here's some work, where do you think we can go from here? What can we make out of this? And that's probably the coolest thing for me because it gives me a chance to interact with high school students that I know that I would have really liked when I was their age, just to have a researcher come in and look at my very first piece of science and build up those hidden skills as a researcher as well, communicating your work.
That was part one of my interview with Liam Burt from the Australian National University, talking about synthetic chemistry to make wires for even tinier electronics. Listen next week for more chemical adventures from Liam. You can now see the videos of my interviews with James Hayes about odour, Ian Bryce about masks, Bonnie, Kirsten and Martin about the search for life on Mars, Sylvia Vincenzi about brain development, and Dipon Sarkar about food microbiology on the Diffusion YouTube channel. Subscribe and like at youtube.com/c/diffusionradio. And that's all from us this week on Diffusion. Are you a scientist, artist, biohacker or maker who'd like to be interviewed about your work? Would your company like to sponsor Diffusion? Send your contributions, opinions, helpful suggestions and donations to science@diffusionradio.com. That's science@diffusionradio.com. Please like the Diffusion Science Radio page on Facebook and rate the show on iTunes. Tell your friends. Follow me on Twitter @IanWoolf. The news music was Rhinos Theme by Kevin MacLeod of Incompetech.com. I produce Diffusion, which is broadcast around Australia to 28 stations on the Community Radio Network, including Radio Blue Mountains 89.1 FM in New South Wales, 8CCC in Alice Springs and Tennant Creek, 2 MBR in Nambucca Valley, 3 MBR in the Mallee Border districts of Victoria and South Australia, City Park Radio 7LTN in Launceston, Tasmania, and 2XXFM in Canberra. Diffusion is now narrowcast on Indigo FM 88 in northeast Victoria. Diffusion is syndicated globally on the National Science Foundation's Science 360 internet radio station and also on astronomy.fm. Subscribe to the podcast on the Diffusion website, www.diffusionradio.com. That's www.diffusionradio.com, and check the website for links, photos and videos about this week's show. If you enjoyed the show, you can explore more than 1,000 previous episodes, archived on diffusionradio.com, where the shows are labelled by keywords so you can focus in on the stories you want to hear. Join my patrons at patreon.com/diffusionradio. Make a donation through paypal.me/IanWoolf. I'm Ian Woolf. Join us inside your audio device of choice for more science wondering next week on Diffusion Science Radio.
Science is fun. It helps you to learn, to know, and to appreciate. When you study science, you may go on field trips. You discover the marvelous interrelationships between all living things. You learn to read the history of the Earth as it is written in rocks and fossils. You find out what makes things tick, everything from a molecule to a living organism. In the study of science is found the most useful and satisfying knowledge of man. Knowledge of his physical world, its past, its present, and its future. And in your moments of relaxation, now and in the years to come, you will find the study of science leading you into fascinating pursuits. Photography, collecting. Why study science? Study science because you will find in the study of science a richer, more rewarding life.